So here we go to continue on with our discussion of temperature and heat transfer. We're going to be looking at what's called calorimetry, which is the flow of heat energy, thermal energy through materials to bring them to an equilibrium, and as well as phase changes, which is changing the state of matter through heat energy. Here we go. Okay, so we can transfer thermal energy from one object to another through a process we call heat. When we do that, we can increase the temperature of an object, which is just the average kinetic energy of that object. The amount of heat energy then that raises the temperature of 1 gram of a substance by 1 degree Celsius is called specific heat. An alternate definition of specific heat is that the amount of heat that raises the temperature of 1 kilogram of a substance by 1 Kelvin. So this specific heat is a way that we can talk about heat energy. The symbol for specific heat is capital C. It's in units of joules per kilogram degree Celsius or joules per kilogram Kelvin. So everything has its own specific heat. A large specific heat, and a substance with a large specific heat, requires more heat energy to change the temperature. Something with a small specific heat needs less heat energy to change the temperature. So heat is energy, okay? It's thermal energy. Specifically, it's the energy that's transferred between a hotter object and a colder object. Specific heat is a property of an object. Okay? It doesn't use the word heat in the same way. Specific heat is it's an old idea dating back to when heat was thought to be a substance that was contained in objects. So the term has been continued in use even though our understanding of heat has changed. So specific heat is a property of substances. Now, because specific heat is a property of substances, that tells us then that different materials will heat up at different rates. Gold, for example, takes about 7 times faster to heat up than aluminum does. And because it takes different rates in which to heat things up, that means that different materials will store different amounts of heat energy. For example, water takes about 30 times longer to heat up than gold does. So water holds about 30 times more calories of heat energy. So the amount of heat energy that's required to raise a substance's temperature is directly proportional to this specific heat, and also the mass and temperature change of that object. So here we have an equation we use to talk about the heat required to raise a substance's temperature, where Q is the heat, M is the mass of the substance, C is the specific heat of that substance, and delta T is the temperature difference. This leads us to be able to talk about the law of heat exchange, okay, where two systems that are placed in thermal contact, which remember that just means that they can exchange thermal energy. So when they're placed in thermal contact, they will transfer thermal energy until their final temperatures are the same. The heat lost by the hot system is equal to the heat gained by the cold system. So we can say that Q lost is equal to Q gained. So we can take this equation and the one substance here and the specific heat of that substance and the temperature difference, the temperature change for that substance is going to be equal to the mass, specific heat, and temperature change of the other substance. Okay, so this is worth taking a look at a basic example of calorimetry. If we have a 235 gram gold ball at a temperature of 125 degrees and we drop it into an insulated flask of water, that water initially at a temperature of 22 degrees. And if the equilibrium temperature is 25 degrees, which means that the gold ball decreases its temperature to 25 degrees while the water increases its temperature to 25 degrees, we want to know what is the mass of the water. So this is calorimetry, okay? The amount of heat that's lost is equal to the amount of heat that's gained, and we get this from this equation here. So we're going to take the mass of the gold ball times the specific heat of the gold ball times the temperature change of the gold ball. That's going to be equal to the mass of the water, specific heat of the water, and the temperature change of the water. Now this is where we have to look up the specific heat of these substances. And looking at page 6 on your reading packet, you'll see 2 tables of specific heats. One of those tables has the specific heat in units of joules per kilogram degree Celsius. The other has a specific heat in units of joules per kilogram Kelvin. Depending on what temperature you are given, what temperature scale you're given in the problem will determine which of those tables you use to find the specific heat. If you're given the temperature in degrees Celsius, you would use the specific heat that is given in units with degrees Celsius. If you're given the temperature in Kelvin, you're going to use the other table for specific heats. So that's why we get a specific heat for the gold of 129 and the water of 4186. So what ends up being the mass of the water is 0.24 kilograms. And we can easily extend this problem into fluids, right? We could start talking about what was the weight of the water. Multiply that by 9.8 and you get a 2.352 newtons weight of that water. We could also ask, hey, what's the volume of that gold ball, right? Well, because, density, we know, equals mass over volume, we could figure out the volume of the thing by taking the mass times the density. Because the volume of water that is displaced, of course, is the volume of the gold ball. Okay, so let's talk about phase changes now. A phase change involves a substance going from one state of matter to another. So melting, for example, is a solid becoming a liquid. Solidification is liquid becoming a solid. Vaporization is liquid becoming a gas. We've got condensation, sublimation, and deposition as well. Now, normally when we add heat energy to a substance, its temperature increases. This is what we expect to happen. Think about putting a pot of water on the stove. You turn the stove on, heat energy goes into that water, it increases the temperature of that water. We call this type of heat energy sensible heat. When we go to try to figure out then something about sensible heat, we're going to use MC delta T. So you're just going to keep in mind that when temperature is increasing, that's sensible heat, and we use MC delta T to figure out something about sensible heat. Now, when an object is undergoing a phase change, heat energy is still involved, but that heat energy is doing something different. It no longer increases the temperature. All of the energy that we put into or take out of during a phase change is involved in putting together, changing bonds and that sort of thing in that substance. Now, some phase changes require heat input. You have to add the heat energy to make that phase change happen. Those changes are said to be endothermic. So that's like melting and vaporization are endothermic phase changes. We have to put energy into it to make it happen. Other phase changes require a release of heat or giving off of heat energy. So those are called exothermic phase changes. Condensation and solidification are exothermic. They release energy. Now, while a substance is changing state, while it's going through the process of going from a solid to a liquid or from a liquid to a gas, its temperature remains constant. Heat energy is still being added to cause that phase change, right? But it's called latent heat. Latent meaning hidden heat, okay? So the heat that is needed, that heat energy that's needed to cause or reverse vaporization is called latent heat of vaporization, which is often shortened just to heat of vaporization. And the heat energy that's involved in melting or freezing is called latent heat of fusion, or just shorten that to the heat of fusion. So the heat required for a phase change of a substance, then, is given to us by Q equals mL, where the Q is the heat energy, the M is the mass of whatever substance we're talking about, and L is the latent heat for that phase change. It's either going to be latent heat of vaporization or it's going to be latent heat of fusion. And every substance has a different latent heat of vaporization. For helium, for example, the latent heat of vaporization is 20.9 kilojoules per kilogram, whereas the latent heat of vaporization for nitrogen is 201 kilojoules per kilogram. This is just talking to us about how much heat energy is required to change the state of matter of a substance. So to help us understand this, right, we can get a visual by using what's called a heat or temperature curve, okay? So let's imagine that we've got a pot of ice, and that ice starts at negative 20 degrees Celsius. We're going to take that pot of ice and we're going to put it on a burner, and we're going to heat it up until it all becomes steam. While we do that, we're going to graph the heat energy as it changes. That is, as the water changes. Now, as we look at this graph, right, anywhere where our line slopes, that's an increase in temperature. What that's telling us then is that the energy that we're putting in is going to change the temperature of that substance. It's all sensible heat. So we would use MC delta T to figure out how much heat energy is being put into that pot of water. Everywhere where the graph is flat, that is a phase change is happening there. And what's happening, what this is telling us, is that the energy that we're putting in is going into pulling apart those little ice bonds, right? Making the thing into liquid water. And then here it's changing the water bonds, right? And ripping them all apart and making steam. It's boiling the water. So in those places, we're going to use Q equals ml to figure out how much heat energy is going into changing the phase or the state of matter. So, here we've got sensible heat, then we've got a latent heat, then we've got sensible heat again, then we got latent heat again, then we got sensible heat again. Now, to look at a little more detail, right, the temperature right here at this point where the substance, the ice, then goes from solid to liquid. And when that phase change begins, we call that the melting temperature. And the temperature over here where that water begins to become steam, right? So we call that one the boiling temperature. And from all this, we could take a certain amount of a substance and a solid and figure out how much total energy would it take to get it to begin boiling or to get all the way to becoming a gas or something like that, or go the reverse direction as well. We're going to see this and examples of this more in class. We'll see you then.